Okay, so on Thursday, we had looked at how artificial gravity can be generated by having some part of a spacecraft or the entire spacecraft be a spinning drum, okay? Just like your gravitron, okay? The ride that they have at Stampede. So what we do in principle is we just make this drum spin around really, really fast so that your inertia wants you to go straight, but the spinning drum prevents it. And by preventing it, it is exerting a force directed back towards the center. Okay? That centripetal force is being provided by normal force. My inertia wants me to leave the circle, so I push on the floor. Okay? But then the floor pushes back with an equal and opposite force, okay, in the direction of the center of the circle. Makes it feel like I have weight. I don't. I'm still weightless. Okay? I don't actually have real weight due to gravity, but I feel like I do. My body won't know the difference. Okay? It's just, in fact, your body won't know the difference because gravity on Earth is really just the normal force you feel from the Earth against your feet anyway. Okay? So your body won't know the difference even though there isn't any gravitational force. Now, this normal force, okay, we still use this formula here to calculate our centripetal force. We want our normal force to feel like what? What force am I simulating here? Force of gravity. All right. How do I calculate that? M times g. All right. So this is the setup for artificial gravity. mv squared over r equals m times g. That'll allow me to figure out how fast I need to make the drum spin for its size. Okay? Its size would be governed by whatever its radius would be. Okay? And then what's going to happen to mass when I start manipulating here? Right. Is that important? Well, actually, it is important that it cancels because that way everybody feels the same effect regardless of their mass. Okay? Because really all we're trying to do is make the centripetal acceleration, v squared over r, equal gravitational acceleration. That's why mass ends up canceling off. Okay? Everybody with me there? All right. So that was the idea, and that's been the idea for probably close to 100 years. Okay? We just haven't been able to make it work yet. Okay? The mechanics of it, they're simple enough. The practicality of building it is a little bit different. Okay? So we haven't done that yet. But all of our kind of modern sci-fi movies all show this as being the way that in which gravity is generated. The Martian has the spinning drum, okay, all of that kind of stuff. But the idea goes back a long way. In fact, so far as to be in a movie from the late 60s. Okay? I think I told you about this 2001: A Space Odyssey. Okay? So 2001: A Space Odyssey was directed by Stanley Kubrick. Anybody heard that name before? If you like really, really weird, out there movies, he's probably directed it. Okay? Like if you've seen The Shining, okay, that's Stanley Kubrick. All right? This movie is nearly 3 hours in length and has less than 17 minutes of dialogue. There's a lot of breathing and silence because, well, art, I guess? I don't know. It's just weird, okay? But it's a good movie, okay? So I'm going to show you a couple of clips from it just to give you an idea of kind of what they thought things would look like in 2001, so like before you were born. It's now in the past, but we'll show you that, okay? And as well as some of the really, let's say, really good practical effects. This is pre-CG, so none of this stuff is done on computer. It's all done with models and practical effects and all that. But it holds up, and it's all fairly physically accurate. But now before I start showing them to you, I want you to put yourself in the movie theater of 1968. Okay? So imagine you're a person in 1968. You don't have a phone that fits in your pocket. Your phone is something that goes on the wall at home. And that's the only place you have one. Okay? A TV is a piece of furniture that's usually encased in wood and sits in one place in the house, not on the wall. Okay? And it's small. It's maybe 20 inches. And it's square, not a rectangle. Okay? It's a very different time. Okay? And put yourself in there and then look at what they're showing on here, because if you look at it from your eyes, you're going to be so. Okay, so what? Okay, we have all that stuff, but they didn't. Okay, all right. All right, so the surface of the space station provides a normal force that's working against your inertia, that's your desire to leave the circle, pushes back, okay, with a force that feels like gravity but really isn't. Right? So if we're doing this as an example, what speed must the surface of the station, with a radius of 1,700 meters, move so that the astronaut standing right here would feel a push that on his feet that equals his earth weight? Right? So we just said a minute ago that we want that centripetal force to feel like gravity, even though it's being provided by the normal force. Okay, so that's mv squared over r equals m times g. Okay, so if I'm trying to solve for v, okay, I've got to do a manipulation. Obviously, m is going to cancel, r is going to come over here, okay, multiply both sides by r, and then what? Square root. Okay, so the square root of GER will equal v. All right, so v will equal the square root of 9.81, because we want them to feel like they're at home, okay, times the radius, 1,700 meters. All right, it's got to spin at 130 meters per second, roughly, 129 meters per second. Is that pretty fast? Yeah. And the bigger they get, the faster they have to go. Okay? A smaller one doesn't have to spin as fast. Okay? Remember, we're dividing by a bigger number, right? So we're getting a bigger, we're multiplying by a bigger number. So the bigger they get, okay, the faster they have to spin. Okay? Everybody all right with that idea? That's really all that can come of that. Okay? You're either going to be asked to solve for the radius of the space station or the speed of the space station, and you just have to understand that FC equals FG for artificial gravity. Okay? They're not terribly different. Right? So that's what we just did there. Okay? There's a number of like science fiction things now. Obviously, they're using it a lot more. But the guy who wrote 2001: A Space Odyssey, the book, also wrote a bunch of other books where they use this same thing. One of them about a giant cylindrical spacecraft that comes to Earth. Okay? And the whole inside is habitable, and it's just because it's spinning. Okay? Now, the weird thing for that, talking like Coriolis effect, you guys remember that from Science 10? Where if something is rolling down the Earth, it curves, and it can't roll in a straight line. Well, the same would be true for something in here. If you had a spinning cylinder, water would obviously still evaporate inside, but it would rise only to where? Like on Earth, it just goes up and forms clouds and hangs there and then precipitates back down. But in a spinning cylinder like this, it would only rise to the middle. So you could get a cylindrical cloud, okay, down the middle of the spacecraft in the air, okay? And what you would get is, as rain would fall, a lot of it would end up on either the front or the back of the spacecraft. And as it tries to fall down the spacecraft, because the spacecraft is spinning, you would get a curved waterfall. Okay, so it would fall down. So if this was the circular end of the spacecraft, your waterfall would go like this. Okay, because there would be that grabbing of it as it tries to fall down. Okay. All right, that's it for artificial gravity. Okay, now we're going to look at vertical circular motion, which is how they make the Vomit Comet. That's what they call NASA's zero gravity trainer, the Vomit Comet. Okay, it causes a lot of that. Okay, I'll show you how that all works. Okay, so for vertical circular motion, so now when we're dealing with a vertical circle, it works differently than all the stuff we've been talking about up to this point. Okay, up to this point, we've been dealing with uniform circular motion, something moving in a horizontal circle where the speed is constant. Okay, and if the speed is constant, the centripetal force is constant. When we switch to vertical, okay, what happens to the speed now? It changes, right? It's not constant anymore. It's slowest where? at the top and fastest, the bottom right, because now gravity is playing a part. Okay? So not only does my speed change, but if my speed changes, so does my centripetal force. I mean, it's mv squared over r. So if v is changing, my centripetal force is always changing. Where do I have the least amount of centripetal force? Watch the string as it goes over the top. Right. Okay? Like it almost goes slack if I do it right at the top. Okay? But it's tight at the bottom. It's tight at the bottom because not only do I have the inertia of the tape wanting to leave the circle pulling on the cord, but I've also got gravity pulling on the cord. At the top, all I have is the inertia of the tape. Okay? If I'm just going fast enough to keep this thing in a circle, there's actually no tension in the string. Now, if I go faster than I need to, obviously there is tension in the string. Okay? But I still have it going faster at the bottom. Okay? But for a vertical circle, there's a minimum speed that you have to go in order to stay in the circle. If you don't achieve that minimum speed, then you can fall out of the circle, which is important if you're doing the loop. Okay? If you're trying to like run a vertical loop, okay? You have to have a certain speed to achieve that. Okay? All right, so vertical circular motion is not uniform. First thing we need to understand. Okay? Forces that contribute to vertical circular motion: gravity, and either tension, if it's something on a rope, or normal force, okay, if it's on a track, because you would push on the track and the track would push back. Okay? And understand that for vertical circular motion, centripetal force equals forces in minus forces out. In other words, Fc is net force, the vector sum of all forces. Okay? And we only have two directions, out of the circle and into the circle. Okay? Everybody follow me there? So anytime you have a vertical circular motion problem, it's forces in minus forces out. Okay? So you'd have like mv squared over r equals, and then whatever your forces are. Okay? If you're in certain places in the circle, it would be normal force minus gravity. In other places in the circle, it would be plus gravity. Okay? It all depends on where you are in the circle. Okay? All right. So motorcycle stunt drivers often try to do this loop, right? This stunt where they go through the loop. If you're on a roller coaster, it's really easy. Okay? Roller coasters go through vertical loops all the time. It's fun. It's the kind of the exciting parts of the ride. But roller coasters also have wheels on both sides of the track for safety. Okay? If you try to do this like on foot, like to actually run the loop, you have to go really fast. Well, actually, it's not really fast, but you have to go straight uphill. And it's really hard to run really fast straight uphill. It's even harder to run really fast when you're upside down. Because when you push on the track, you want to go towards the middle, which is falling. Okay? So you have to build up enough speed that your inertia essentially carries you through the circle. Okay? Does that sort of make sense? All right. Now, I'm going to show you a couple of applications of this. If it wasn't for YouTube, we would have no idea how generally stupid everyone is. Because those kind of things you would never hear about, but now you get to watch it. It's awesome. Okay, so if we're looking at a vertical circle, okay, we're only going to be dealing with essentially three places on a vertical circle. We're going to be dealing with the bottom on the inside of the circle, the top on the inside of the circle where you would be upside down, and the top on the outside of a vertical circle. Okay? And the reason we're only going to be dealing with those places is because you can't be here. Okay? Like if you were on a roller coaster hanging upside down in the bottom of the vertical loop, that is lawsuit after lawsuit, death after death. Okay? Not because the cart would come off, but because if you were upside down and stuck on this loop, all the blood would rush to your head violently, causing blood vessels in the brain and eyes to break. Bad. Okay? Here you have a blackout. Here you have a red out. And red outs can be deadly. Okay? So here on the bottom of this vertical circle, people might lose consciousness. Not the end of the world. They'll regain consciousness. Okay? Why do they lose consciousness here? Yeah, exactly. All the blood rushes away from your head to the bottom of a vertical circle, right? The inertia is trying to pull it away. Gravity is pulling it away from your brain. And if you're going fast enough, it's enough to starve your brain of oxygen and you'll pass out, okay? Like this guy. All right, so when we got a vertical circle, okay, if we're looking at these three situations. We're not going to look at the sides, because on the sides, gravity doesn't play a part. On the sides, it's like uniform circular motion because gravity is perpendicular and is not acting either into or out of the circle. So we don't ever deal with those 2 points. But we deal with on top of the circle and we deal with on the bottom of the circle. Okay, top or outside and inside at the top, but only inside on the bottom. Now, if I'm looking here at the bottom, where would I feel heaviest? Yeah, on the bottom. That's where you black out, okay, on the bottom. Okay, reason for that, gravity is pulling out of the circle. Your inertia is this way, which takes the blood away from the brain, and then the seat or the track or whatever it is you're on is pushing back towards the middle. And it's got to push harder than this because the net force needs to be into the center of the circle. If it's not, then you won't stay in the circle. Okay, so this is where you would feel the heaviest. You aren't actually any heavier, but you feel heavier because the normal force pushing back on you is way greater than it would be if you were stationary. Does that make sense, everybody? Yeah? Okay. If I'm going around like the guy we watched run it, okay, he's on the inside of the vertical circle. And at the top, you have gravity pulling in, okay? And if you go just fast enough like he did, that's all you have, is just gravity. But if you're on a roller coaster and you're going through a loop, you're going faster than you have to stay in the circle. So your inertia pushes on the circle and the circle pushes back. And so you'd actually have two forces acting back towards the middle. Okay? If you're going over the top on the outside, gravity still pulls in, but what pushes up? So I'm sitting on a track. Okay, gravity's pulling me into the track. What's the track doing? Pushing back. So my normal force acts out of the circle at the top. Okay, now it's in this position that you can feel weightless. This is what the vomit comment does. Okay, you feel weightless as you go over the top of the vertical circle. Okay, you've all felt this if you've gone over that speed bump out there too fast. Okay, you feel like everything inside you is coming up. Okay, if you go over a hill really quickly on a country road, okay, you get that sensation. Well, that's because of your inertia. Your inertia wants to go like this in a straight line, okay, but gravity is pulling you back. If you go fast enough, you're not going to. But if you went fast enough over that speed bump, what would happen? You'd launch. Okay, if you launch, okay, then you are going over a different circle. And if you launch, are you touching the ground anymore? Okay, if I'm not touching the ground, I'm not pushing on the ground. And then the ground isn't pushing on me. How do I feel? Weightless. Yeah, if I don't have any normal force to tell me how heavy I am, I feel weightless. Okay, and that's how you would feel if you were to launch off of a jump, okay, off the top of a vertical circle. You'd feel weightless until your car came crashing down and destroyed itself. Okay, incidentally, I've seen that happen on that speed bump. Yes, okay, yeah. So don't do that. It will, your car will bottom out and things will catch on the ground and be ripped from it. Usually vital things like transmissions and oil pans. Yeah.
So does that usually get me like to drop at the step or
Similar, except that's just an elevator. It just drops quickly, and so you're accelerating due to gravity. Anytime gravity is the only force, you feel weightless if there's nothing to push back, right? And that's what's going on here. If you go faster than you need to, you essentially become a projectile, right? And then there's nothing to push back. Yeah. All right, so that's what we're looking at here, okay, when we're going through a vertical circle. So you feel heaviest at the bottom, and you feel lightest, okay, at the top. You could also feel weightless on the inside at the top. Okay? If you're going just fast enough to stay in the circle, the only force acting would be gravity, and you're essentially a projectile, okay, for an instant that's following that arc.
Did they do that for like a music video? They went really high up on an airplane and then they just dropped it? And
Yeah, the problem with just dropping an airplane is it rips the wings off, right? You don't want an aircraft to fall. So what it does is it goes over the top and then just plunges, right, like nose down. And so for that period of time, you feel weightless. But then it has to pull out of the dive, and you actually feel 2 times gravity as it pulls out of the dive and goes back up, right? Right, so there's actually a long period of time where they accelerate for that, and then just 30 seconds as the weightlessness.
If a roller coaster was to go like straight down, it's different than if you're like sitting up and going down. If you know what I mean?
I do know what you mean, and the answer is sort of yes and sort of no. If you're just in free fall, so if I'm on a ride where, like the space shot, for example, like West Edmonton Mall, right, where they shoot you up and then drop you down, you feel almost weightless while you're falling and when you're suspended at the top. Because when you're suspended at the top, your inertia is still carrying you. And that's why you can see in the pictures of people, if they have long hair, the hair is up. Because the ride has stopped and you keep going. So you lose contact with the seat and you feel weightless. And then it shoots you back down, so you're falling almost at 9.81. It's actually about like 8 point something, so you actually do have some normal force, but you feel weightless. And then when you stop at the bottom, it's like, ugh, and you hit this, you know, you feel something really heavy at the bottom. And then when it's shooting you back up, you feel really heavy because it's pushing really hard on you to make you go upwards again. That sort of makes sense? If you're on a roller coaster, it's oriented differently. So you're not oriented like this, you're oriented vertically, so you don't feel it in the same way. It's the same action, but you don't feel it the same.
So it's kind of the same as the airplane going
Yeah,
down.
it's more like the airplane. Yeah. Okay, so if the speed changes, okay, the magnitude of the centripetal force changes because, as we were saying, centripetal force equals forces in minus forces out. Okay, so at the bottom of the circle, okay, centripetal force equals, so if we're down here at the bottom, normal force is pushing in, and gravity is pulling out. Okay, that's at the bottom. Right? If I'm on the inside at the top, okay, Fc equals forces in, gravity, okay, plus normal force, because they both act in. Okay, so if I'm up here on the inside, gravity's pulling down, which is towards the center. Normal force is pushing down, which is towards the center, and there are no forces out. Okay, so you'd have, in that case, you have forces in and no forces out, so there's nothing to subtract. And then if you're on the top, on the outside, centripetal force equals forces in. This time it's gravity pulling in minus the forces out. Normal force. Okay? If you go fast enough, there is no normal force, and you feel weightless. Okay? So a question ever says, you know, it's going so fast that it loses contact with the track or the road, then normal force is now 0. Because if you're not in contact with the surface can't push on you. All right. So this is like, I don't know if anyone had these Hot Wheels, orange Hot Wheels tracks when they were a kid. They built these for real cars. Okay, so people could live out their childhood dream of driving upside down. Okay. And so yeah, if you go fast enough, yeah, you can make your car go through the loop. I would not recommend building something like that. And it's a lot of engineering and stuff that goes into that, like welding and stuff like that. Probably shouldn't mess with it. Yeah. Okay, so this is what we were just talking about. For vertical circular motion, it's always forces in minus forces out. What you have to decide is which forces are in and which forces are out, based on where you are in the circle. Okay? So that's what we were just looking at there. All right. So I'm going to show you the Simpsons Ball of Death. I'm going to go see the Simpsons movie. It's getting to be an older movie now, but okay. This is one of the times where the Simpsons does something right and it's fun. Now, if you're going through a ball on a motorcycle, okay, and trying to go over the top or under the top of the vertical circle, you have to maintain or at least achieve that minimum speed, just like the guy who was running did. Okay, so when Homer is going up this sphere, he's got to go faster as he gets towards the top. If he doesn't, he'll. Okay, so we're talking about the top on the inside. Okay. What are the forces acting if you're going just fast enough to stay in this circle? Just gravity. Right. There's no normal force because I'm going just fast enough, so I don't push on the track. The track doesn't push on me. It's my inertia at the top that pushes on the track, and I only have that if I'm going faster than I have to. Okay, this is going just fast enough to stay in the circle. Okay, so Fg is acting towards the center. So when we say Fc equals forces in, that's gravity, minus forces out. There aren't any. Okay, so if we're calculating the minimum speed to stay in a circle, we're just looking at this. And when we manipulate it, it's just like the artificial gravity questions we did earlier today. Okay, because we feel, or actually we are, weightless at that point. Okay, the m's are going to cancel, g or r is going to come over here, and we're going to square root. Okay, so to calculate the minimum speed of a vertical circle is g times r. So 9.81 times whatever the radius of the circle is, square rooted. Okay, will give you the minimum speed for the inside of that loop. Okay, that's the only place where there's a minimum speed, because obviously you can't fall out at the bottom and you can't fall out going over the top. Okay, and there's no minimum for those, you just stay on. Okay, questions on that? So tomorrow we're going to look at a lot of problem solving. Today we got the old fun stuff. Okay, tomorrow we're going to look at a lot of problem solving, okay, to do with vertical circles, okay, and we'll have a quiz tomorrow, which I'll post at 3:20. Okay, so you can have a look at that. Question? Okay, also reminders, guys, of the things you have coming due this week. Your speed and radius lab is due December 1st. Centripetal Force lab due December 3rd. Your Unit 3 exam will be December 14th. Okay, I'm just telling you when it'll be. We'll probably be done the unit before that. Okay, so you can plan around it. And your final exam, because that's been posted now, okay, is January the 24th. Okay, and it will be somewhere in the science wing, probably this room, but I don't know that for sure. Okay, and that'll be at 9 a.m. So make sure you're planning around that as well.